So, welcome back. Now you should have an idea how the automated or assisted parking works. And you should have also considered what is the optimization objective in trying to make the car to collide. And you should have also considered what are the test cases or the test inputs that you try to improve. If you have not already done so, you can pause the video now. Okay, so the optimization objective in this case has been to minimize the distances that the car has to the curb or to the area where it cannot park, and also to minimize the different areas to the collision that the car can have. And these are good optimization objective because they are continuous. Now, often in search-based testing, the sort of discontinued software behavior need to be turned to continuous. And this continuous behavior would be car collides or it does not. But when we measure the distances or areas to the collision, this is a continuous. And even further, if you go to other kinds of search-based testing problems, the thing that software is not very linear often results in problems. I mean, you have if statements, loops, and it usually results in complex, discontinuous or non-linear search spaces. So this is one of the challenges of search-based testing, is how to turn the optimization problem in a way that it is continuous space. So once it's continuous, then you can start to use the different sort of evolutionary algorithms on it. Okay, now we understand what are we trying to optimize for. What is our fitness function? What is our measure of quality we are aiming at? So what are we trying to then optimize? What are the tests and what are the inputs? So you can basically see them on this figure. So we are running this in a simulator, so there is possibility to modify different things in the parking scenario. And these are the test inputs, these are the test cases we try to modify. So there is the space width, which is basically, how wide is the space where the car is supposed to park. How long is the space vertically. Then the distance to the space, where does the car start from, this gap to the collision area, and then finally this angle where this car is currently located at. So this is the test case. These are the test inputs that you try to vary. And as you run this in a simulator, it's easy to run it in a way that you just start out with different space width, space lengths, distance to space gap, and this angle. And of course you put, in this case, of course you put in some boundaries so that the space length is always longer than the car. Or maybe you don't. Maybe the car software should figure out on its own that it doesn't fit into this square and then try not to park in these cases. But you might set some boundaries or you might not. And here are some examples of the distance computation. So this is the, on the figure you can see that this is P3, which corresponds to this P3 spot here. This is the P4, and then this is P5. So this is the distance computations on different parking scenarios. So we can see that on scenario 1, the distance looks like this. The distance is greater than 0. Then here the distance is 0. So the car just passes through this corner, and in this case the distance is less than 0, means that the car cuts this corner, and the test cases therefore have been able to find a collision. And this here is the area to this P2, P3 plane. So we can see here the area is greater, and these spots, I assume that they are always the minimal distance to to the plane, or particle spot in the plane, because the car is not shaped like this. So this is the minimal distance over time. And we can see here area is greater than 0. Then again we have the 0 case, which means that the car just touches this plane, and then we have the collision case where the car goes over this area here. Okay, now we understand the basic components. Now let's see how their entire system works. So here is their evolutionary testing loop from their later paper from 2008. And here we start from the initial population phase on the top. So typically you initialize the population at random. What does this mean? Initialize population at random. Basically you take up the starting test cases at random. So you initialize all these values: space width, space length, distance to space, gap, psi. You initialize them at random. Then the next step, fitness evaluation. Okay, so what is the fitness evaluation? So it's basically these distance measurements. Did it collide? How far off was it? If it wasn't collide, what was the minimal distance or the minimal area? How close to the 0 are we getting? Then there's the question of termination. Obviously not very relevant in the first round, but this could be based on things like, okay, are we able to make the cart collide? So maybe you want to stop every time you make it collide. Or maybe you have a time-based termination. So for example, let it run for 1 hour and then check the results. So next step is selection. So you basically best select the best individuals for the next round. And what is the best? Well, you look at the fitness function, which ones are the ones that minimize distance, minimize area. So which test cases minimize these two? So you select them for the next round. Okay, now we cover the genetic algorithm operation: selection, recombination, and mutation. Okay, here's another slide on this evolutionary loop. So we already initialized with random values. Space width, space length, distance to space, gap, and psi. So these abbreviations all come from this figure. You just read them from left to right. SV short for space width, SL short for space length, and so on. So initialization was done, fitness was evaluated, and then the best ones were selected for reproduction. Okay, so what is this reproduction? So basically, two parents, two well-performing parents, two best individuals, will have an offspring. They will have a child based on some probability. And here we have an example of parents P1 and P2. And we can see that for P1, all the values are initialized to 10. So the space width, space length, distance to space, gap, and everything is just initialized for 10. This is just for the purposes of this example. And then we have another parent that has all these values initialized to 20. And they could have offspring, they could have children with crossover, and it would look like this. So the first offspring would inherit these genes, space width, space length, distance to space from parent 1, and then it would take, from parent 2, it would take this gap 20 and psi 20. And then another offspring might have this reversed, or it might have different combinations. So this is how the test cases or the population has babies in this genetic algorithm. Okay, now we have explained the recombination phase of this algorithm. Now the next step is mutation. So now there is, in the population, we have some offspring and we have some best parents that survive the first round and some of their children. So then next step is to do mutation. So let's assume that this parent 1 has these values as previously, but there is a mutation in the gene. So with some probability this PSI value gets a new sort of random value within the boundaries that are set for this PSI value. And why is this mutation step here? Well, basically it avoids the local minima or local maxima. So if the chromosomes, which are these individual values of the test cases, become too similar to each other, this would slow down or even stop the evolution. So if for some reason all of the offspring and all of the parents, for example, let's assume that all of them have PSI value 10. So for some reason this gene has been very good, this PSA value 10. But this is not optimal. I mean, this would get you stuck in the local minima, and we don't want that. We want those sort of radical jumps that we also saw with the simulated annealing. So we want some randomization, some jumps there. So then there is this mutation step to prevent this from happening. Okay, and now the final step. We have the recombination, which is producing offspring, producing children. We have the mutation of the parents and the children, and then there is replacement. So you can have different replacement values. For example, you might replace 50% of the previous round's population with offspring. So you would keep 50% of the best parents, do the recombination, make them have babies, and replace the 50% of the worst. And then you do fitness evaluation, you figure where it's trying to terminate, and then you just run this loop again and again until it's time to stop. Okay, and this is basically it. Now you should understand how the genetic or evolutionary algorithms work in this case. And as pointed out, this is a part of the meta-heuristic search algorithms. Genetic algorithm, genetic programming, evolutionary programming, differential evolution, that sort of are inspired by how genes and nature and the sort of survival of the fittest has worked in the evolution of this planet. So they are inspired by those sources.